As the most direct source of experience, the mind continues to fascinate and inspire efforts to understand its inner workings. Our technical society, PolyCortex, is an interdisciplinary team which brings together students from Polytechnique Montréal and the University of Montreal who unite their love of cognitive science with their unique abilities to use technology and develop real-world practical applications. Electroencephalography, or EEG, is such a technology which provides high temporal resolution and convenient means of determining some of the key changes that go on inside of our brains. Before the activity of the brain can even begin to be decoded or interpreted, a fundamental step of EEG consists of gathering biosignals from the scalp using electrodes and guiding those signals through a series of hardware and software processing. It is this crucial step which we strive to achieve as contestants in the fixed challenge component of this year's NeuroTechX Student Club Competition. Our latest fully homemade acquisition pipeline for EEG-signals builds upon our previous designs. It features an ambitious and significantly optimized 4-channel acquisition printed circuit board, as well as a Python-based, fully redesigned real-time EEG visualization and processing software which allows stunning frequency bands power characterization, data storage, and much, much more. Advanced software and electrical design can require skills acquired over several years of study and experience. This past year was a particularly fruitful one for PolyCortex, as our desire to innovate was equally matched by a recognition of the need to continuously grow abilities of all our members. For example, skill transfer activities yielded the production of 2 simpler PCBs, each one incorporating key components of a complete EEG acquisition board.
Now to our main acquisition PCB. Much as was true of our previous submissions to the NeuroTechX competition, our team once again strived to both meet and excess the design requirements. In consideration for what we achieved previously, we also set ourselves to the task of improving upon our other designs. Accordingly, several new components and features were added to perfect our pipeline's analog signal processing capabilities. EEG signals collected with electrodes may contain EMG information from the subject's muscular activity and ECG-signals from the polarizing cycles of heart cells. Towards preserving all relevant EEG informations, it was decided to maintain signals within a bandwidth ranging from 0.3 to 35 Hz. In order to achieve the desired bandwidth filtering needs, the first filtering stage consists of a second-order Butterworth high-pass filter. Likewise, a second-order Butterworth low-pass filter with a cutoff frequency of 35 Hz helps ensure the removal of EMG signals and other noise. Main power line interference is one of the major factors which can adversely influence the quality of the acquired EEG signals. A notch filter was included in the design to adjust the main hums of 60 Hz and is configured to produce a simulated gain of about -36 decibels. Placed directly after the electrode's input, an instrumentation amplifier provides the signal with an initial gain before it is being filtered. The amplifier is a high-performance, low-power, rail-to-rail precision amplifier, providing a gain of approximately 40. Towards the same end, the operational amplifiers used in the high and low-pass filters configuration allow each filter to provide an additional gain of 8.9. After the signal has made its way through the instrumentation amplifiers and the filtering levels, it is amplified a final time with a non-inverting operational amplifier offering a gain of 12.8. The total gain produced by the cascading of the instrumentation amplifier, the high-pass and low-pass filters, and the non-inverter is thereby the multiplication of each individual gain, providing a final gain of approximately 41,000. To ensure the communication between the circuit and the visualizing software, the voltage of the 4 channels must be converted from analog to digital. The ADC was selected with its 4 channels input, its high sample rate, and its significant common mode rejection ratio. The output of the ADC is directed to an Arduino microcontroller so that it can be imported into our Python-based software. In previous versions of the EEG acquisition circuit, the amp ops were supplied with 5 volts and saturation was observed while gathering EEG data. Instead of decreasing the overall gain of the circuit, PolyCortex decided to increase the power supplying the circuit. The net positive power supply of the circuit was thus set to 9 volts and the negative one was set to -9 volts since the board is powered with 9-volt batteries.
To ensure the circuit behaves as it should, all filtering stages were simulated with LD-Spice, and the final amplification, as well as the filtering capacities, were both tested. To test the filters, AC analysis was used and allowed visualization of the circuit frequency response between the start and stop frequency and displaying of the bulb plot. Transient analysis was used to test the complete circuit over a given channel. Such analysis allowed the visualization of the nonlinear transition response of the circuit in the temporal domain, much like an oscilloscope would.
As you can see, the electrodes are connected to my forehead, and the current travels to the card where the electrode input is located. And then we have the instrumentation amplifiers here, and then the current travels to the operational amplifiers where the filters are located in the notch filter. And then we have a final amplification right here in this operational amplifier chip. And then the current travels to the ADC, which is connected to the Arduino microcontroller. From the Arduino microcontroller, we have a connection to the computer where the signal is displayed in the time domain on the left here over 4 channels, which are connected to my scalp. And then on the right, we have the frequency domain where we can see some activity in the lower frequency range where we have a bandpass filter.
The total cost of the board with its components is $243. The board itself was ordered online from PCBWay and printed out for the cost of $141. The total cost of the components, which were ordered on DGK Electronics, is $102. Our competition effort this year yielded not 1 but 2 EEG acquisition PCB designs. While our main submission is aimed at correcting previous concerns and offers more than incremental improvement, we wish to also introduce a prototype design. The prototype proved more complex to manufacture and test than our other designs and forced us to consider enhancing our assembly methods. Its several new components and features, including common mode chokes, a right leg driver RLD circuit, and RL filters, make it one of our most ambitious designs yet, and we hope that it will inspire our future submission or others in their PCB designs efforts. The real-time EEG visualization software was completely redesigned as part of our fixed challenge submission. The software is Python-based, object-oriented, fully open source, and was originally developed using EEG-signals input from an OpenBCI Katon acquisition board. With our own PCB, data is received from the connection to an Arduino Uno R3 microcontroller. Using the competition PCB, the sampling frequency is limited by the capabilities of the ADC, which has a specified 6,250 Hz sampling rate. Owing to recent development in the field of machine learning and in the minute signal processing opportunities that are derived from it, the software is equipped with a convolutional neural network training module. The module was tested with EMG recorded using the Saturn board, and EMG detection capability can be demonstrated through a featured signal classification-based game. The software offers a variety of informative and pleasing visualizations options. Of course, time and frequency domains for each channels are on display. Also included are a graph of the evolution of individual average frequency bands over time. The software also features a 3D scalp time domain EEG visualizer and 2D and 3D spectrograms facilitating characterization of the eye-closer paradigm. The time series data can be exported as a CSV file for subsequent static analysis. A conversion factor, which depends on the hardware used, is applied to the signal data to recover initial preprocessed signal voltage values.
With help from all our sponsors, to whom we offer our deepest gratitude, this year our group of university students was able to greatly expand the knowledge base and abilities of its members. We were also fortunate to have benefited from truly outstanding and inspiring participation and contributions from our members who continue to challenge themselves to learn and innovate and pave a way for our future endeavors. In making our methods open source and demonstrating our progress, we hope that future generations of engineers and neuroscientists will gain an appreciation for neurotechnologies. It is a great honor to be a part of and compete in a student competition with our peers from other institutions internationally. We look forward to continuing to grow alongside them and as part of the NeuroTechX community.